Energy Switch is the popular point-counterpoint show where two leading experts with different perspectives discuss the most pressing energy and climate issues in the news today. Next on Energy Switch, carbon capture and storage.
Funding for Energy Switch was provided in part by the University of Texas at Austin and by EarthX.
One solution to reducing our carbon emissions is to capture them and store them underground. There are challenges in all steps of this process. How to capture the CO2 at energy and industrial facilities, how to build the pipelines to move it, where to store it, and how to pay for it. But there are many projects, now in their early stages, beginning to address these issues. I'll talk about these with Sallie Greenberg. She's the principal scientist for energy and minerals at the Illinois State Geological Survey, piloting a carbon capture and storage project at Illinois' ethanol plants.
It's more about being an emissions mitigation suite of technologies. So if it's cement factories, if it's ethanol, all of the above, we need to be decarbonizing those point sources.
With her, Julio Friedmann is the chief scientist at Carbon Direct, a carbon management company, formerly with the U.S. Department of Energy and Columbia University.
If you care about climate, you should care about carbon, period. 20 years ago, we were just looking at coal plants, for real, maybe gas plants. Now, we have capture technology for everything, and the costs are going down fast.
I'm Scott Tinker, and I'm an energy scientist. In this episode of Energy Switch, carbon capture and storage. It's great to have you both here, and we're starting off with why. What do we care about capturing and storing CO2? Why does it matter?
If you care about climate, you should care about carbon, period. The math is in. We can do some things like electrification and renewables and nuclear, but there's a bunch of things where we cannot do fuel switching, where we just make emissions. It's about 1/7, about 14% of climate can really be best addressed with carbon capture.
Okay. Agree?
I agree. I think we have safe, effective, demonstrated technologies that allow us to remove significant amounts of carbon dioxide from the system, and we need to deploy it now.
Yeah. Well, let's talk about it. There's lots of components to it. You know, capture is the first part. Coal plants, these are the big emitters. How do we go about doing that?
Basically, what you need to do is separate out the carbon dioxide from everything else that's in the emission stream, which is typically, somewhere between 7 to 30% carbon dioxide. So you need either a membrane, which is a physical separation mechanism, or an amine or a chemical separation, so that what you end up with at the end of the day is pure carbon dioxide.
Okay. You got this stream going up a stack, and you're grabbing the CO2 out of that somehow.
Yeah.
Does it make sense at coal plants?
There are two places in the world where we do this from a coal-fired power plant, one in Canada, one in Texas. But otherwise, we're doing it from stuff like natural gas refineries or hydrogen facilities, mostly from industrial sites. So today, there's about 27 plants around the world capturing about 46 million tons of CO2. And we have injected something on the order of 500 million tons of CO2 in total. So we know how to do this.
So 46 million tons per year they're capturing?
Yeah.
Okay. And so you said 46 million tons. Just for scale, how much do humans emit every year?
We do 46 million tons of CO2 globally. Global CO2 emissions are about 40 billion tons.
Yeah.
So we're doing 1/1000th of that today. And that's one of the big challenges with carbon capture.
Yeah.
It's a big prize, but we got to scale it up a lot.
Yeah. So let's talk about gas then. Natural gas is growing. It's got some benefits to capture. Talk about it a little bit.
The biggest cost associated with capture is the separation. It's not the capture. If you capture from ethanol, it's 99.9% CO2 and some water. It's very easy to separate that out, and you have a pure stream of CO2. So the capture cost there is low. But when you are capturing either from coal or natural gas, you still have that high separation cost. So gas burns cleaner, obviously, so you have less particulate matter. That helps us in other ways. Whether or not it makes an impact in terms of carbon capture and storage and the ease, I'm not so sure.
Okay.
We're seeing a big change right now in the way that we're capturing from natural gas. Yeah, you can capture post-combustion at a power plant, but increasingly we're seeing people make hydrogen out of natural gas. And you can separate the CO2 out before it gets burned. And the hydrogen burns clean and it burns cheap and it burns hot. All of these are things that we want. So if you want a clean fuel like hydrogen, natural gas with carbon capture becomes a very useful option.
Yeah, that's interesting. How do we capture from other types of things? Cement, petrochemicals, refineries, besides power generation. How do we go about that?
You know, in a lot of cases, it's simple separation. Ethanol, you're putting a capture unit right on your fermentation system. I mean, the fermentation of corn produces carbon dioxide. You capture that, you divert it to a compression dehydration system, which carbon dioxide is a compressible gas. So and it's wet when it comes off of fermentation. So you want to compress it from atmospheric pressure to, around 1,000 PSI. And, you use ethylene glycol to knock out water as you go through your compression stages. Depending on where you're capturing from and the engineering of the plant that you're capturing from is what is going to make the difference.
Okay.
20 years ago, we were just looking at coal plants, for real, maybe gas plants. Now we have capture technology for everything. We are capturing CO2 at steel mills. We are capturing CO2 at cement plants. We are capturing CO2 from the air.
Yeah.
From the air, like we did in submarines and spacecraft for a very long time. All of this is now climate relevant. Yeah. So we've got this new fleet of technologies that have come out, and the costs are going down fast. In the last decade, the costs have been dropping 50%, and the next decade, they're going to drop another 50%.
Yeah.
It's more about being an emissions mitigation suite of technologies, not so much what is the source of the CO2. So if it's coal plants, if it's natural gas-fired power plants, if it's cement factories, if it's ethanol, all of the above, we need to be decarbonizing those point sources.
So there's a portfolio of sources.
Yeah, absolutely.
Refineries, gosh. Sallie, you've got a project going. Talk about that a little bit.
So the Illinois Basin Decatur project was funded by the U.S. Department of Energy through the Regional Carbon Sequestration Partnership Program, started in 2008 and just finished up. It demonstrated the full value chain of carbon capture and storage. We captured 1 million tons of carbon dioxide from ethanol production at an Archer Daniels Midland corn processing plant over a period of 3 years. A second project leveraged all the science from that, and that project started injecting CO2 in 2017 and is still injecting today. Okay. So all told, there's probably about 4 million tons of carbon dioxide stored in Decatur.
4 million tons is a lot. Is this scalable? Are we going to start to see things like this?
I mean, where we started was individual projects, regional assessments, building capacity and proving that we could do this safely and effectively. What we're seeing now is the development of the infrastructure and the ways that we're going to connect this so that across the country, we're connecting sources with storage locations.
Yeah. We talked a lot about point sources. You mentioned direct air capture. Mm-hmm. The mechanics of it, you're moving a lot of poor volumes of air through something in order to scrub out something that isn't very concentrated in them. Is that why it's so expensive?
Exactly. Direct air capture, because of the super low concentration in air, you just have to build it differently. Yeah. You can't do the same thing you'd do for a point source. What you end up having to do is make a really big air contactor, because you got to touch a lot of air.
Right.
That costs a lot of capital. And then you have to reconstitute a lot of solvent or sorbent, which is also expensive.
Yeah.
Right?
Yeah.
And most of the energy cost is not electricity. Most of the energy cost is heat. So you got to pay for heat, which is its own thing, right? So direct air capture is helpful for things that we have no technology for, like the use of fertilizer emits greenhouse gases. We're going to keep using fertilizer. We don't have an option for that. Mm-hmm. Aviation's going to cost something like $2,000 a ton or more to abate. Carbon capture from the air is about $500 a ton now. Right. So it's just cheaper, right? And those costs are coming down fast, too.
Yeah, one of the things that we're seeing is the concentration of these kinds of technologies. So I think what you're going to see is direct air capture infrastructure located perhaps at a storage site, or you're capturing from a facility and you're installing direct air capture either at the capture end or at the storage end because you are increasing the capacity and you have a system to move it.
Yeah. Why do we care about capturing and storing CO2? What's it used for?
Well, the main use is enhanced oil recovery, where we're using carbon dioxide essentially as a solvent to help us produce additional oil from mature oil reservoirs.
Yeah.
And those activities, depending on the price of oil, are only limited by the amount of CO2 that is available to them.
Is the net equation okay on that, or?
I think you need to ask Julio about that.
You can completely balance the CO2 produced from oil with the CO2 injection. That is only a thing recently. People have only wanted that as a product in the past few years. We are also seeing a whole lot of new uses for carbon dioxide. One of those is to turn CO2 into concrete. Concrete's the most used material after water in the world. We use 30 billion tons of concrete a year. You can put a lot of CO2 into that. Increasingly, people are also looking to turn CO2 into fuels and chemicals. So there's a company out there called LanzaJet. They take the waste CO2 from steel mills and turns it into jet fuel, which is pretty cool.
What's the energy equation on that? Is it?
This is the thing. To do that takes more energy than was in the fuel to begin with. But there's a bunch of companies that turn CO2 into everything from vodka to Legos and yoga pants. And it's nice that we can reimagine a world made out of this waste product.
Yeah. One or two most promising, Sallie, that you've seen?
I think construction material, wallboard, things like that, makes a lot of sense instead of mining that stuff. And I think cement.
What about plastics? Any use coming down the road there?
Yeah, absolutely. And a number of companies are looking to make CO2 into precursor chemicals, things like ethylene and carbon monoxide or methanol, and then those get turned into plastics.
Right.
I'm going to add, we're not going to balance the climate books on yoga pants, right? The entire plastics market in the world is about 1 billion tons a year of stuff. So you can maybe get 100 million tons of CO2 into that.
Yeah.
Okay? It's not that much. The entire concrete business is 30 billion tons. You can probably get 1 billion tons of CO2 into that, maybe 2. That's
real.
it. It's real and it counts, but we know the arithmetic.
Right.
We emit 40 billion tons of CO2. We're going to have to stop emitting in a bunch of places, and a bunch of that CO2 is just going to be stored.
So let's talk about storage. How do we do that?
We start with the geology. One type of rock, for example, sandstone, has pore space in between the grains of sand that make up the sandstone, and then that is capped or sealed with something much denser like a shale.
Yeah.
So you look for sedimentary basins where you have that kind of package of rocks. You characterize it, try to make sure there are no faults and fractures. After you've captured your carbon dioxide, ship that via a pipeline, you drill wells in the subsurface, and then you basically inject that carbon dioxide through a well into a reservoir, into a rock reservoir.
And those are filled mostly with?
Brine, heavy brine, salt water.
Old oceans, right?
Yeah, and so you're talking about water that's not potable, and so carbon dioxide, some of it goes into solution, it dissolves into the brine itself. Okay. Some of it exists as discrete CO2, just pure CO2 in its liquid form.
So kind of trapped in its phase.
Yeah, trapped in its phase. And it gets stuck in those pore spaces.
And people have to remember, what you're putting underground is not a gas. It works like oil in the subsurface. Right. So any rocks that would normally trap and store hydrocarbons will do the same thing here.
Yeah. Is that safe? Is that?
Yeah, absolutely. I mean, here's how we know that you can store things in the earth for hundreds of millions of years. Because we can produce oil that has been in the earth for hundreds of millions of years, and we're creating a storage complex that takes everything we know about oil and gas production and turns it around to make the safest storage container that we can.
Yeah. There's some CO2 pipelines around. Where are those, and why do they exist today?
So there's about 5,000 miles of CO2 pipeline in the United States. The majority of that is in the West. There's also significant pipelines from Canada, North Dakota, but mostly I would say out out west and the southeast.
Yeah.
We are, in fact, seeing purely privately financed pipelines come into fruition. That is the consequence of policy changes in the U.S. That tax credit 45Q pays people to store CO2. And these pipelines that are springing up around the Midwest, in aggregate is like 30 million tons of CO2. It's a big number. And we're glad to see this stuff happening.
Right, right. 5,000 miles sounds like a lot, but compare that to natural gas pipelines. Any numbers there?
Yeah, the natural gas pipeline network of the United States is 2 million miles, so a little bigger. And analysis has shown that to get all the stuff we care about with carbon capture in the U.S., we need somewhere between 20,000 and 60,000 miles. But it's not ridiculous growth. Like, it's totally in bounds.
It's not 2 million miles.
Yeah, it's not 2 million. Now, these are pipelines. CO2 is corrosive. You can't just put it in a natural gas pipeline, right?
Well, it's a mix of stuff. The CO2 plus water is what's corrosive. CO2 on its own isn't. It has to be pressure rated. You want certain kinds of metals in the pipeline. You don't want to use cast iron. But you can use some of the existing infrastructure, but not enough. We're going to need to build a bunch of pipelines.
We don't like building pipelines. We seem to be opposed to building pipelines.
People love to hate a pipeline.
How are we going to do it?
So
Can we do it?
Yeah. So one of the things that's been looked at and has been suggested is specifically permitted corridors that are developed by the federal government where you're aggregating multiple types of pipelines. There are CO2 pipeline companies. The challenge there is how flexible you are in the routing of your pipeline and whether or not you may invoke eminent domain.
Right.
And what we see in the Midwest is that you have people who their identity is wrapped up in that land, their legacy, their wealth, and their stewardship. I mean, they feel very strongly about the stewardship of that. And so it's a really challenging social construct that you have to look at.
Similar to building big power lines.
Yeah.
I mean, should we be scared of CO2 pipelines? Should the public be scared of these things?
No. CO2 puts out fires. Like, it is something our body makes. It is the most inert, benign substance like around, you know. Its energy content is the same energy content as water. Like, it is not like an oil pipeline or a gas pipeline or a hydrogen pipeline or an ethylene glycol pipeline. Like, it is a pretty benign substance. So the risks of these things is actually quite low.
Yeah.
There are reasonable concerns that people have, and you got to address those concerns.
One of the big things that I hear when I talk to people is, why can't we have more safety valves or more safety monitoring equipment at shorter intervals? And I don't think that those are unreasonable questions or demands.
But we've built 2 million miles of other pipelines. We've done this.
Right. The fact is, at some point or another, we're going to have to bite the bullet. We have to build infrastructure for the energy transition. And it's not just CO2 pipelines. It's transmission lines and ports and charging stations and fueling stations and all these things. So we have to get into a way of saying yes to projects like this. Because otherwise, we are just not going to hit our climate targets. We're just not.
Yep.
And I just want to make the point about the energy transition, and that is that we're at the beginning of the energy transition. We have not actually accomplished an energy transition. And so all of this willingness to do hard things and to have these complicated projects, like, that's all part of what we have to be willing to take on.
I mean, everything we're talking about, it's all money. How does this happen?
Let's start by saying in some markets, in some parts of the world, you won't do carbon capture. Japan and South Korea, they just don't have places to store CO2. But this gets paid for because you care about climate. That's all it's for.
Right.
As it becomes urgent to move forward, you'll see that carbon capture is cost competitive in a bunch of markets and a bunch of applications.
And what countries are the most promising?
Norway has been at the forefront of this space. They've been storing carbon dioxide in under the North Sea since 1995. Australia is a leader in this space.
But these are rich world. Does it make sense in emerging, developing world?
I think it makes sense for everybody to look at all options available to them.
It is fair to ask if for some developing nations, carbon capture should be a priority. And because carbon capture and storage has additional cost, for some nations, it's not practical for them to do that today.
Yeah.
I'm thinking about a nation like South Africa or Nigeria or Mexico. Maybe that's not their priority. In a place like India, it may not be a priority today, but it will be soon. So they should start the work of planning the geological assessments, looking at technology options, thinking about how to finance it. They should start that now.
Yeah.
But I'd just like to add to that, it's not like those countries are completely unaware or completely disengaged from the conversation. Obviously, they have much, much more immediate challenges that they're facing. But I think that there are certain countries that have done, for example, the geologic assessment of what the potential for carbon storage is onshore and offshore.
The US, Europe could do more in terms of engaging these parts of the world. I would like to see something that looks like a Marshall Plan in which instead of just giving money to countries for aid, we give money to domestic companies to deploy in those other countries. That is exactly what Japan does today. They are trying to invest in places around the world where they can bring carbon capture into them to benefit their industry. And that industrial policy has got a new life these days.
You mentioned earlier, Julio, CO2, 40 million tons now, not that much, a 1,000-fold increase, I think you said, plus or minus. Is it possible?
So 100 times scale up is super hard. It is no harder than the other super hard things we have to do in the energy transition. It is no harder than tripling the electric grid. It is no harder than a 400-fold scale up in clean hydrogen. It is no harder than hundreds and hundreds of nuclear power plants all over the world. All of these things are hard. It is just one of the incredibly hard things we need to do if we're serious about climate. But there's nothing in the finance or the physics or the engineering that can't be done.
Closing thoughts, Let's pretend like you're a benevolent dictator for the day.
Love where this is going.
What should be our plan of action for carbon capture? What would you do, Sallie?
I would force a balanced portfolio. I would say, how do we use everything that we have for the greatest benefit for the greatest number of people? And that looks like what works best where. How do we deploy at micro scales and macro scales? I love this idea of trade agreements or some sort of international policies that allow us to bring other countries along. And but I would also solve the local problems. And I really believe, at the end of the day, having hard conversations is the path to get there.
Same question.
Later on, I will hand you my 70-point plan on what to do. But if I have one thing to do, infrastructure is the thing we're missing. For the next 30 years, every week is Infrastructure Week in the United States and around the world. We need to build ports. We need to build transmission power lines. We need to build hydrogen fueling stations and CO2 pipelines. We need a lot of infrastructure we don't have. If we are clever and inventive and generous in how we do that, the Global South can benefit in a big way, and the world will benefit from that. And we will see geopolitical rearrangements from such a thing if we're smart about it.
Great stuff. Thanks.
Thanks.
Great dialogue. Our guest said that initial projects to capture CO2 at coal power plants have not been so successful. We've gotten better capture results at ethanol and fertilizer plants that produce a purer stream of CO2. Other pilot projects are capturing CO2 directly from the air, though at a high price. CO2 emission sites are widely distributed, so we'll need pipelines to reach them. There are currently 5,000 miles of CO2 pipelines in the U.S. Permitting new ones will be challenging. Storing the CO2 may be more straightforward. Oil and gas has been trapped in subsurface reservoirs for millions of years. Research has shown that injected CO2 will remain there as well. These experts agree that new infrastructure is vital to connect the places that could capture CO2 to the places that could store it.
Energy Switch is executive produced by Scott Tinker and produced and directed by Harry Lynch. Emily Hooks is the assistant producer and researcher. Editors are Ginny Patrick, Yusef Swachina, and Jackie Kunzler. Matt Aslanian does the sound. Energy Switch is produced by Arcos Films for the Switch Energy Alliance, with support from the University of Texas at Austin and EarthX.